Hello everyone. Today is the first class about for the thermal physics and statistical mechanics, the semester 3 paper. And for the entire paper, we are going to follow three approaches, namely thermodynamics, the kinetic theory of gases, and statistical mechanics. Thermodynamics deals with macroscopic properties such as pressure, volume, and temperature without worrying about the underlying microscopic property. The kinetic theory of gases, as the name suggests, is talks about the kinetic, that means about the motion of individual molecules. That means we are considering the microscopic approach. This kinetic theory of gases is the microscopic approach in which we are going to follow the motion of each of the microscopic constituents of the system. Statistical mechanics, as the name suggests, mechanics, that means we are going to talk about motion, and statistical means we are going to follow about statistics. In this approach, rather than starting with the description of macroscopic properties as in thermodynamics, we are going to describe the individual microscopic states of a system and then use statistical methods to come to macroscopic properties from them. Thermodynamics, as already discussed in the previous slide, we're going to talk about macroscopic properties, the properties which are easily visible, the properties which are visible to naked eye, which are easily understandable. If That means if you're talking about a mechanical system, the properties like pressure, volume, and temperature, which are easily measurable. Thermodynamics is an empirical science. The word empiricism has a literal meaning that knowledge proceeds from experience. That means in thermodynamics, we are not going to do some hardcore derivations or some hardcore mathematics. The laws of thermodynamics are based on simple common sense logics and simple experience. For instance, when we put our hands in hot water, we know that we are going to feel hot. We know that we might burn our hands. This is coming from experience. Even a person who doesn't know science or who doesn't understand the laws of heat would simply not put his hand deliberately into hot water because of the fear of burning them, and that is coming from experience. This is how the thermodynamics, which is based on empirical laws. The other two approaches, kinetic theory of gases and statistical mechanics, as already discussed, kinetic theory is focusing on motion of individual molecules. Statistical mechanics is also focusing on those motion, but it is using statistical methods and we are arriving at the macroscopic properties. Now for the first part of this paper, we are going to follow the thermodynamic, that is the macroscopic approach. Right now we are going, once we have decided the approach, now next we need to decide what we want to study. And simply what we want to study is known as system. System is part of the universe which we have chosen to study. And surroundings is as simple as that. Surroundings is everything else apart from the system. For instance, if I want to study this particular class, that is BSc Physical Science third semester, then this is my system, and physical science chemistry fifth semester and first semester and other courses in the college like history honors, chemistry honors, they are part of my surroundings. And in this particular diagram, as you can see, this is a very typical diagram of a cylinder which has a piston and which has some gaseous molecules in this. This particular gaseous molecules constitute their system. This is, and everything apart from the cylinder, that is your surroundings. This particular system has a specific physical boundary, that is the walls of the cylinder, which separate this system from the surroundings. That means you can clearly physically define the boundary. But for a system which I just mentioned, like the physical science chemistry, there is not physical boundary, but you can clearly understand there is some sort of boundary which is you can understand that, which you can imagine that, right? And obviously the definition of surroundings also depends on the definition of your system. If I consider, instead of considering physical science third semester particularly, I take a bigger set, that means I consider your physical science chemistry whole, as in the first semester, third semester, and fifth semester, then my surroundings would obviously change. Now, physical science fifth semester and first semester cannot be a part of my surroundings since they are part of my system. So, the part of surroundings would be the other remaining courses and of other remaining years. So, we have to be very clear what we want to study will constitute the system, and everything else which may or may not affect it would be the surroundings, and this total of system plus surroundings is your universe. System can be of three types. It can be open, closed, or isolated. An open system means which can interact both with energy and matter. That means a system which can exchange both energy and matter with the surroundings is known as an open system. Closed system can exchange energy but will not exchange matter with the surroundings. Isolated system will not exchange either energy nor matter. Now when we are talking about interactions, we will be focusing on two different type of interactions, the heat interactions and the work interactions. For example, if I go back to my previous example of the system, the heat interaction could be that I would simply put a burner in below that cylinder and heating the gas in the piston. That would be the heat interaction. The work interaction would be that the expansion of gas is taking place. It is important to note that both these interactions can take place simultaneously or they may take place separately also. But one important thing is, in the end, we cannot distinguish. For example, let us consider an example of heating of hands, right? If you want, suppose it's very cold and you want to heat your hands, you have two options of doing so. You can either do by rubbing your hands or going near a fireplace. But in the end, once your hands are pretty warm, they're warmed up, you cannot distinguish that whether you heated your hands by rubbing them or whether you heated them by going near a fireplace. Now we're coming to the most basic law of thermodynamics, that is the zeroth law. This was given by R.H. Fowler. Now when we talk about zeroth law, the first thing we should come to your mind is why zero and why not first? It's an important reason about this is that before the first law and the second law were discovered, or you say formulated, before the zeroth law of thermodynamics. And since they were so popular in their form as in the first law as second law, so it wasn't good to change their order. And the zeroth law was found to be even more basic than the first and the second law. So thus, thankfully, thanks to Aryabhatta, that we had a zero and we could have a number preceding one, and that we could have zero. And what's this zeroth law talking about? It is talking about thermal equilibrium. For us, thermal equilibrium is a very simple word. Thermal equilibrium for us simply means something that if you're talking about thermal equilibrium between two systems, then we simply understand that they must be having same temperature. But when we're talking in the 18th century, when this law was formulated, then there was nothing known as temperature. Then we have to go back to that century and try to understand what was thermal equilibrium in those terms. In those terms, thermal equilibrium was, that means if the two systems are in thermal contact and there is no transfer of heat energy from one system to another, then the systems are said to be in thermal equilibrium. And zeroth law simply states something which is pure common sense. That means if A and B are in thermal equilibrium, and also if B and C are two systems that are in thermal equilibrium, then that would simply imply that A and C are also in thermal equilibrium. That was pure common sense. And this is from the zeroth law we comes the concept of temperature. That means temperature was found to be the parameter, that temperature was found to be the quantity or the parameter which would be constant for these particular systems which are in thermal equilibrium. So when we are defining the zeroth law, we cannot use temperature in that definition, but temperature comes out as outcome of zeroth law. Temperature is the parameter which is same for the systems having thermal equilibrium. And what is thermal equilibrium? Thermal equilibrium means that in thermal contact there is no heat transfer from one system to another. Now we need to describe a system, thermodynamic system. Then obviously we would need some parameters. Parameters are of two types, intensive and extensive. It's very important to remember this. I'll just help you. Intensive, remember this IN. This intensive parameters are independent of the extent of the system. For example, pressure and temperature. Extensive obviously are dependent on the extent of the system. We just understand by this example. There's a system A, and what I do is I put a wall in the system and I break it into two parts, system A1 and system A2. Then let y be some parameter for system A, y1 be some parameter, the same parameter for system A1, and y2 be the same parameter for system A2. If your parameter is intensive, that means it was not dependent on the extent of the system. That means since nothing has changed, we have just put a wall in between them, the value of parameter y would remain same for all these three. That means y equal to y1 equal to y2. But if your parameter is extensive, that means it is dependent on the extent. Since you have broken the system into two parts, the system value in system A should be sum of value of that particular parameter in system A1 and system A2. That is y equals y1 plus y2 for an extensive parameters. For example, whatever was the volume of system A, that would be obtained from V1 and V2. Now we are talking about thermodynamic equilibrium. Before understanding thermodynamic equilibrium, we need to understand three different types of equilibrium: thermal, chemical, and mechanical. Thermal, as we have understood, that they are at same temperature and there is no thermal heat transfer from one part to the other and from the surroundings to the system. Chemical equilibrium means that there is no sort of chemical reaction, that means no chemical constituents are moving in and out of the system or within the system. Mechanical means that there is no unbalanced force in the interior of the system or between the system and the surroundings. When all these three equilibriums are satisfied, then the system is said to be in thermodynamic equilibrium. Now we're talking about the first law of thermodynamics. First law of thermodynamics is essentially a statement about conservation of energy. Very important. It's a statement about conservation of energy, which simply what is the conservation of energy? That energy can either be created, not be destroyed. It can only be converted from one form to another form. It is also very important that it is the first time that we understand that heat is a form of energy, right? Before that, in the 17th century, the 18th century, the Joule's caloric theory of heat was of prime importance. And what was that? Heat was considered to be an indestructible fluid known as caloric. That means a system which had more heat would be having more amount that of that caloric. Then it was Rumford who showed that heat is not any caloric or any liquid, it is energy in transit. To describe first law, we would need to know what is internal energy. Internal energy is the sum total of internal kinetic energy and potential energy of the constituents of the system. From the first law of thermodynamics, we are going to understand how the changes in internal energy can be accomplished. They can be accomplished by thermal interactions, that means heat entering or leaving the system, by mechanical interactions, that means work done on the system or work done by the systems, or the diffusive interactions, that means matter moving in and out. This is the mathematical expression of the first law of thermodynamics. Kindly note the difference in del adjacent to your Q, the difference in D adjacent to U, that is your internal energy, and your del. This del indicates that heat and work are path functions, and this D indicates that it is a perfect differential. That means the quantity adjacent to it is a perfect differential and is a state function. And what is the difference between state function and path function? Path function is simply like we're talking difference between distance and displacement. Path function is the function which is dependent on the path undertaken, but the state function is dependent only upon the initial and the final states. For example, if I tell you to have a round in your park or in your college ground, two rounds, just enter from one gate, have a round, and leave from that particular gate itself, then what would be the work done? If work would have been a state function, then work would have the net work should have been zero. But that is not the case. Obviously, you have spent some work, you have spent some energy, you are tired, you are sweating, right? The work is not a state function. Similarly, about heat, but internal energy is a state function. But just an important point to note is adiabatic processes. Although we have not discussed about different type of process, but just a brief mention, we'll be discussing about the processes in the next class. Adiabatic process means a process in which there is no change in heat. That means del Q, which is change in heat, would be 0. So du will be equal to del W, right? For that particular case, for adiabatic gases, the work done becomes a state function only for that particular case. So we'll just wind up this class by simply again stating the first law of thermodynamics, which states that the amount of heat entering a system can either be used to change the internal energy or perform some work, right? This In this particular paper, we are going to follow the notation that Q would be positive when heat is entering the system and would be negative when heat is leaving the system. Del W would be positive when work is done by the system and negative when work is done on the system. So simply conservation of energy, that whatever heat is being entering, it can be used to change the internal energy or can be used to perform some work. Like if we eat something, either we can store that energy in our body or we can perform some work immediately. So this brings us to the end of this particular introduction class. We would proceed with the different types of processes and the applications of first law in the next class. Thank you very much.